Each year, an average of more than 2 tons of concrete is poured for every man, woman, and child on the planet. That makes concrete by far the single most utilized engineering material on Earth.
Concrete is a very, very good construction material for many reasons. It's relatively inexpensive. It can be formed into different kinds of shapes relatively easily, and its ingredients are widely available. The one shortcoming is the brittleness of this material.
In an experiment conducted by University of Michigan Civic and Environmental Engineering professor Victor Lee, the steel reinforcement rod embedded in this structural model was pulled upward. The concrete in which it was anchored shattered. The outcome was much better for Professor Lee's bendable concrete, called engineered cementitious concrete, or ECC.
This is what we call plastic behavior. So the material provides a give under very extreme loading instead of fracturing into pieces and still hold the load.
ECC's bend but don't break approach can result in safer buildings.
That's how we got started in this work, to enhance structural safety under extreme loading, such as during a major earthquake event or during even man-made disasters like bomb blast, for example. We would like to keep the occupants safe.
Another test, conducted by research fellow Mo Lee, measures bending loads on a horizontal span.
This is a normal concrete specimen under bending load. So here on the bottom of the specimen will be under tension, and the top of the specimen will be under compression. You can see that it has very sudden failure, which corresponds well to the catastrophic failure mode of concrete structures.
Achieving catastrophic failure on the ECC sample takes 4 times as much force, and it displays over 300 times the ductability, or bendability, of the standard sample. And while failure for the standard sample means snapping in 2, the failed ECC stays in 1 piece. The secret lies in adding coated microscopic fibers that work together to share the load.
You can see those tiny little cracks formed here. Those cracks are so little that they are as tight as human hair.
According to postdoctoral research fellow Aaron Sekulich, there's a side benefit to trading one big crack for many smaller cracks. Turns out, bendable concrete is also self-healing.
This is the kind of crack that you would see in regular cement or regular concrete. It's fairly wide. And then down here is a crack that started out much smaller and it was able to heal much better. All concrete has some capacity for self-healing, but in normal concrete, that doesn't work because the cracks are all very, very wide.
And what kind of exotic chemicals does it take to heal these micro cracks?
Water and air, which fortunately, especially here in Michigan, we have plenty of both.
And like any place that has 4 seasons, Michigan has plenty of cracks and potholes on roads and bridges. Part of the problem is that roads are made of a combination of concrete and steel, and when steel rusts, it expands, a process that can be accelerated with a small electrical current.
120 hours after the current started, the concrete cracks, and it cracks to a very severe extent so that basically it just fractures the concrete. You can see the corroded steel inside. This is basically what happens often on a bridge deck where steel is corroded because of the presence of water and de-icing salts.
And while standard concrete failed after 120 hours of the accelerated corrosion experiment, the ECC sample remained intact after 3 times as much exposure.
Here's a very small micro crack showing up, and here's another one where the corrosion material comes out. So it experiences damage because of the corrosion of the steel, which expands around it, but it accommodates that expansion by being able to plastically yield.
So for states with only 2 seasons, winter and construction, just how long might a road made with ECC last?
What we are hoping to achieve with this newer material is to extend the service life to as much as 100 years.
Concrete that bends, heals itself, and makes buildings safer, and roads that can last 100 years. What could possibly be next? How about smart roads that could tell you how they're doing?
With the ability of self-sensing, the structure will always know and report its condition so that repair can be done only when and where it is needed.
An infrastructure that's safer, more durable, and more sustainable. Sounds like a good road forward.